Welcome to the ad hoc CAP seminar of the summer. It's my pleasure to welcome and introduce Jennifer Lee. Jennifer was a graduate student here. She got here, I think she was admitted the first time, right when I got here the first time I was on grad admissions. I think Felipe was for all names, yeah. And she graduated in 2021. She went to University of Michigan and is now currently a Schmidt AI Fellow. And she's going to be talking about AGN.
Can people hear me from the microphone? Good? Yeah. Okay, great. I'm very happy to be back in town. It feels kind of weird, but also a lot of fun. Currently I'm a Schmidt AI and Science Fellow, and we have like 20 postdocs from different fields like, biochemistry, aerospace engineering, and we collaborate on different kinds of projects, including like writing a paper about using ChatGPT for research or doing data challenges just for fun. And so like if you guys want to talk to me about that later, I'll be happy to talk about it. But today I'm gonna mostly talk about my research on AGN from different scales, like from CGM to the accretion disk scale. And I'm just really interested in AGN in general, so I just kind of work on different parts of it throughout different parts of my career. And most of these are on different types of survey, and I'm gonna talk about why I'm particularly interested and excited for Rubin LSST in the near future. Yeah. So starting from the hierarchical structure formation framework, right? We know mass built on like small density fluctuations from the early universe, and it eventually formed like stars and galaxies and clusters in the local universe. And so at the center of these large dark matter halos, we have, the clicker's not working again, but it's okay. I'll stay here. There's a massive galaxy in the center, and in that center, we have a supermassive black hole. So when this supermassive black hole is actively accreting, it becomes an active galactic nuclei. About 10% of these AGN forms a radial jet, so we call them radial loud AGN. And because there are a lot of gas clouds and dusty torus around the center of the AGN, sometimes we don't really see directly into the innermost structure of the AGN. So if we're looking directly into the accretion disk at the center of the AGN, we call these like type 1 AGN, meaning it's not obscured. And then if we're looking from an angle here, we call it type 2 AGN, which is obscured AGN. And the most luminous population of AGN are also called quasars. So today in my talk, I'm mostly going to talk about type 1 AGN and mostly quasars, but I'll just use the term AGN and quasar interchangeably a little bit. Yeah. So at a local universe, we see this very tight relation between the properties of the galaxy bulge and also the center black hole. So from the early 2000s-ish, people discover black hole mass is correlated to, say, the bulge mass of the galaxy, or the luminosity of the bulge, or the velocity dispersion. And so this very tight correlation leads to the foundation of AGN feedback and galaxy black hole coevolution. And yeah, this is really interesting because the AGN itself is only like a few light years in scale, compared to the host galaxy, which is a few tens of kpc. But somehow on these drastically different scales, they know about the growth and of each other and kind of step together and then form this tight black hole host galaxy relation at redshift 0, like in the local universe. Yeah. So like I say, a very simple idea to explain this is through AGN feedback. So in the center here, I have this artistic illustration of how gas moves into a galaxy and then also recycled out into the CGM IGM scale. So a galaxy needs a cold molecular gas to form stars. And a black hole needs material to accrete and grow. But from the Kennecott-Schmidt law, we know that a decent gas reservoir of a galaxy would be depleted in relatively short time compared to the cosmic time. And so we kind of need this constant gas supply that goes onto the galaxy to sustain star formation, like we see in the local universe. Yeah, so here there's like, so the relation between the gas surface density and then the star formation rate surface density. Yeah. On the other hand, we also see that only in a dark matter halo, we only see small percentage of the mass eventually become stars and the galaxy itself. And so, so here is a relation between the halo mass across a very wide scale from 10 to the 10 solar mass to 10 to the 15 solar mass. And then the galaxy fraction is maybe like 1% of that total mass. And so there needs to be a mechanism that stops stars from forming so efficiently. And one idea is that AGN could be that feedback form used by heating up or expelling the ISM into the broader scale, like into the CGM or in the IGM. And this also explains how the enriched metal can be expelled into larger scales from the ISM of a host galaxy. Yeah, so thanks to like new wide field sensitive integral field spectrograph, we are now seeing evidence of these kind of AGN fueling and feedback in observations. So here is an example from Muse VLT Muse optical eye view observation. So this is a 1 arc-minute by 1 arc-minute field of view. There is a quasar in the center. This quasar is at redshift 1-ish, and it is a radio loud quasar. And as you can see, there is a very complicated gaseous environment here. You see these giant nebula clumps around the galaxy in the AGN host galaxy group. And then you see this giant filament that spans over 100 kpc that is kind of funneling gas into the host galaxy nebula. So like here, you can see that the velocity field of the filament and the host galaxy eventually connects. And so this made us suspect that there is this filament accretion from the CGM scale into the host galaxy scale. Yeah. This is a velocity. Oh, you mean these things?
On the left, the red contours is what exactly?
Ionized gas and O2. O2 ionized, yeah.
How can you tell the difference between incoming and outgoing?
So from the velocity field, and also in this case, we also have a down the barrel UV spectrograph to actually know incoming and outgoing from the AGN center. Yeah. So another example here is a radial quiet AGN at redshift 0.6. In this group, we mostly see this interaction triggered ionized nebula. So the ionized nebula in O2 and O3 are shown in the upper panel here, and kind of coincides with the direction where we see two different groups of galaxies in the host galaxy group here. So from the velocity dispersion, it seems like there is like two different sets of galaxies that are emerging. Yeah, and in this case, the interesting part is like in part of the spectals we see here, there is a broadened line profile, which indicates there might be some AGN outflow. Yeah. So one thing I'm interested in is to understanding how common these ionized nebula is around quasars, and how do they connect to quasar evolution and forming from the CGM scale to the quasar scale, right? So to answer these questions...
So, can you go back one slide?
Yes.
Or actually, one more?
Yeah.
One more.
Oh, one more? Okay.
Yes.
One more?
There.
Okay.
So, on the Northeast Nebula,
Yeah.
You are seeing emission in
O2.
O2, but there's actually no continuum at all. So there's no, is it true that I can say that you cannot really find the host? It's just like kind of like a nebula gas floating around that is not attached to another galaxy, and this is just like in the continuum. Is that safe to assume?
So the continuum is the grayscale here. There's like a galaxy here. So we're guessing these might be ISM stripped from the host the other smaller galaxies. Yeah.
And before you took these observations with VLT Muse, do you get actually redshifts from some of the other nearby galaxies to? I mean, you knew beforehand that those were, I wouldn't call them members, but maybe at the same redshift.
Yeah. So because it's IFU, so we can measure all the redshifts.
No, I know that you can do it once you get the IFU, but before you actually got the observations, did you have like photosees or something to indicate that there's a quasar here and there's a lot of galaxies that are in the same group? Did you know that beforehand before the observation?
Like this is more like a serendipitous discovery. So it's like
and the last question is like, how strong is your signal on G11, given that probably you only have, you only have O2? Do you have any continuum? Because there's no, there isn't really any host. You're just seeing the nebula. Yeah.
So I'm not sure about G11 in particular. So the G11 here is like a galaxy, but the redshift is like similar to the nebula here. So I'm guessing either there's no continuum to do stellar absorption line redshift, or it's just like blended with the ISM here. Yeah. Does that make sense? Yeah. Good. Yeah. So to answer these questions, we use data from the CUBS survey. The CUBS survey is led by 3 people: Xiaowen Chen from UChicago, Sean Johnson from Michigan, and then Gwen Rudy from Carnegie. But so the CUBS survey itself is a CGM survey. It is designed to census CGM and IGM in the sidelines of 15 very bright quasars around redshift 0.8 to 1. So the core of the CUBS survey is these very high quality cost spectrograph around 15 bright quasars. But to do the CGM survey, we do a galaxy survey around these quasar sightlines. So it is designed in a wedding cake type like survey structure. So at the very deep end, we have the CUBS ultra deep. This is using Muse again for a census around all the galaxies and gas around the quasar itself. It goes down to detecting galaxies of L star 0.0001 L star. And then on the wider view, we have multi-object spectrograph follow-up for all the galaxies we can see in imaging for up to 20 arc minutes. So there are a lot of different science going on in this survey, but I'm mostly interested in the VLT Muse observation here. There's another survey that is very similar to CUBS. It's called Muse Cubes. The design is pretty much identical, and I'll talk about results from both CUBS and Muse Cubes in the next few slides. Yeah. So using the Muse data, we can look at the CGM environment of 30 quasars around redshift 1, and we find that there are a very diverse morphology of CGM scale nebula in these quasars. Some of them have these small, like round-ish emission that is pretty much consistent with just having a host galaxy ISM nebula, but some of these are like really crazy looking. So this one is the cold accretion disk cold accretion I showed earlier. This one is the interaction, and then so this one is also a system where we think there is a lot of interaction. Yeah, so over half of the quasars have CGM scale nebula, and then the other half have maybe a smaller scale ISM size nebula. And a lot of these are driven by galaxy interaction, filamentary accretion, and outflows, and other things. So next we want to look at the group environment of quasars. we kind of identify all the quasar, all the galaxies in a narrow redshift window here to look at how many galaxies are in the quasar host galaxy group. And so some of them are in these very poor groups. There's like maybe 2, 3 galaxies within the quasar host galaxy group. And then some of them are like this. There's like a few dozens of galaxies. Yeah. So this is quite surprising because previously, according to wide field surveys and clustering studies, we also often think that quasars reside in the most overdense regions, especially the radial loud quasars. But here we're seeing that they could actually be in fairly poor groups as well. Yeah. So we can quantify the overdensity by comparing the numbers of galaxies when there is a quasar and also when there is no quasar in the field. And so we did this in the redshift space. So in the center bin here is all of the galaxies within the small redshift slice around the quasar. And then compared to the background here, the stack overdensity of our 15 quasars from Cubs is actually 10 sigma. So like quasars do, in fact, live in overdense regions, but just not all of them do. Yeah, so if we look at the individual overdensity parameter for each of the quasars, you can see that most of the radial loud quasars live in pretty rich groups. Radial quiet quasar seems to have a less overdensity, but still most of them live in above average overdensity.
Sorry, can you go back one?
Yeah. Oh, overdensity here. Yeah, so we stack everything in the difference from their central, difference of redshift from their central quasar. So, and then in the center bin here are the galaxies we believe are in the quasar group. And then beyond that is just like a background. Yeah. Yeah. So we try to see if there is any correlation between the overdensity and black hole parameters. Here we look at overdensity versus black hole mass and over luminosity. And as you can see, this plot is pretty much a scatter plot. We don't see any obvious trend here. Even though our dynamical range is quite limited here, there's like 1 dex of black hole mass, and then from the single epoch black hole mass estimator, we have a systematic of like 0.4 dex. So this is like maybe 2, 3 elements of. Yeah.
Do you have any estimates on the black hole spins?
No. No, it's just for it's black hole mass from single epoch estimator. So it's a, yeah. Yeah, similarly for the nebula properties, we also try to correlate it with black hole parameters. For example, redshift, luminosity, black hole mass, and radial loudness. And here we also see that everything is just sort of a huge scatter, huge mess. Yeah. So it seems like CGM, on a CGM scale, quasars live in pretty diverse environments in terms of all these different group properties, interaction, and gas environment. And so this is only a few dozen quasars we're showing here, but because of there are new IFUs being under constructed and designed right now, we're expecting to do this kind of work a lot in the future, and I'll come back to that a little bit later. Yeah, so that's zoom in to the smaller scale, right? So what happens with black hole host relationship on the galaxy scale? So there has been numerous of work expanding on the early discovery in the 2000s on the local host galaxy and black hole correlation in local quiescent galaxies. And there's been extension of this work onto with local active galaxies and also spiral galaxies and other galaxies. And it seems like, for the most part, at the local universe, galaxy properties and black hole are tightly correlated. However, it becomes less clear what happens when you go up in redshift. So here we're plotting deviation from the local black hole host galaxy relation as a function of redshift. And as you can see, there is a lot of scatter here, and this work, Park L 2015, say there is a redshift evolution. But at the same time, this work actually say that a lot of this is based on, is because of selection bias and luminosity bias. And so it is unclear how black hole relations evolve with redshift. So as part of my thesis work, I led a HST imaging survey using the Hubble Space Telescope to do high resolution imaging for about 38 quasars from redshift 0.1 to 0.8. And so this is part of the SDSS-RM survey, which I will talk a little bit more about later. But the most important thing about this sample is that this is the only sample with direct RM-based black hole mass beyond the local universe, say redshift of 0.3. And so this sample is carefully selected and can be kind of calibrated for selection effect properly. And so in this survey, we use two-band imaging with HST to measure the bulge and host galaxy mass for each of the quasar hosts. And this is a compilation of all the images we have here. So this is our results from the black data points here shows the bulge mass versus black hole mass for the SDSS-RM quasars. And roughly, we can see that it is consistent with the redshift 0 correlations from two different work. And then if we step backwards in redshift, we can see that it also is consistent with higher redshift work with active galaxies, and also even higher redshift around redshift 1. So to look at the evolution more clearly, we plot the black hole mass a deviation from the local relation on the y-axis as a function of redshift here. And the top panel here shows the deviation for the bulge mass. And so we can see that all these work kind of line up around the center, and we don't see an obvious redshift trend here. And the bottom here, I'm showing the host galaxy mass. And the reason why these two samples have drastically different number of sources at high redshift is because a lot of these redshift over 1 host galaxy mass were derived from SED fitting. So in those cases, you cannot differentiate between the bulge and the host galaxy. Yeah, but it seems like there is no evolution up to redshift 1 and even up to redshift 2 or something, according to current results. Yeah, so like I say, this brings me to the part 1 conclusion of my talk. We've looked at AGN environment from the host galaxy to a CGM scale using different kinds of these high resolution sensitive imaging using, say, MUSE and then HST. There are a lot of exciting new studies going on in both of these fields. For example, at Michigan, we have a lot of IFU from optical to near infrared that is currently being designed and deployed and tested right now. So there's the Michigan IFU-M and also MIRMOS in planning. And then in the future, we're trying to build a Harmony on ELT. Yeah. And then on the host galaxy and black hole relation end, I worked on a JWST proposal when I was a grad student here. I believe a few postdocs here are working on the data now. Yeah. All right. So now I'd like to switch gears and talk about the smaller scale on this slide here. So we talk about the CGM scale, the galaxy scale, and then, but all of these observations get us a lot of great constraints on the host galaxy and environments. But one key problem here is that it is really hard to measure black hole mass and black hole properties, right? So how do we, so all these new observation is only half of that equation. So how do we study supermassive black holes and their surroundings? The most straightforward way is to directly stare at them, right? So for example, we can monitor the motion of stars or gas clouds around black holes, like showing here with the center of our galaxy. And by monitoring the motion of the stars here, we can measure a black hole mass. The other way, because with the Event Horizon Telescope, we can directly image some black holes. But all of these methods are really limited by spatial resolution. We can only do this for a few nearby black holes, and this is not going to change in the foreseeable future because we're just limited by how big of a telescope we can build and how big of a baseline we can have on Earth. Luckily for us, there is a very interesting characteristic of AGN, is that they are variable on a lot of timescales and variable on many wavelengths. So this is an example from the AGN NGC 5548. There is X-ray monitoring and UV monitoring from SWIFT, and then UV and optical monitoring from HST. And as you can see, these light curves just vary a lot within a short timescale of this is maybe 100 days. So the x-axis here is time in days, and the y-axis here is magnitude or flux. Yeah, and so each of these wavelengths actually corresponds to a different inner structure of the AGN. For example, the X-ray corresponds to the corona from very close to the supermassive black hole itself. And then the UV and optical corresponds to the accretion disk. And then the optical lines here corresponds to the brown line region around the AGN. So by looking at the light curves from different parts of the AGN spectra, we can actually map out different parts of the inner structure without resolving the structures spatially. So this is the foundation of reverberation mapping. I believe a lot of people here are familiar with the concept RM. So, but to give a quick recap, basically you are looking at two different streams of light curve. For example, here the continuum light curve is from the accretion disk itself, and then the HBL light curve is from the brown line region that is further out of the AGN. And there is a time lag between these two light curves here. So you see the peak to the peak here, there's a tiny shift. And so the time lag roughly corresponds to the light traveling time from the accretion disk to the broad line region. And using that, we can map out the size and then the structure of the AGN and constrain different things like accretion disk structures or supermassive black hole mass and accretion rate. Yeah. So the important thing is this is not limited by spatial resolution, and in theory you can monitor any type 1 AGN if you have the time and resources. Of any redshift. So even though at higher redshift, the lag will be time dilated with a 1+z factor. Right. Since RM requires a lot of observing resources, previous RM studies are often limited by resources. So for example, this is the light curve I just showed in a few slides before. So with NGC 5548, they had to have HST, SWIFT, and a bunch of ground-based telescope point at the single AGN for, say, 100 days, and then get data every day or every other day. And so this is a lot of observation and a lot of telescope time. So even though RM can be very useful, prior to the use of multi-object spectrograph in RM, there's only a few dozen of RM AGN in total. Yeah. So SDSS-RM is one of the first large-scale RM surveys. It started to use multi-object spectrograph for RM. And so the idea is that we are not pointing the telescope at one AGN at a time now. Instead, we are pointing at a few hundreds of them. So with SDSS-RM, we were monitoring 849 quasars in a 7-degree field at the same time. And then the cadence was every 6 days to every 30 days, depending on which part of the survey you're looking at. And because of we had photometric monitoring prior to SDSS-RM starting, the full photometric baseline was 11 years, and then the full spectroscopic baseline is 7 years. So on the right here, I'm showing the redshift versus expected lag from SDSS-RM prediction from almost 10 years ago. This is a US paper from 2015. And so the red points here shows the RM AGN prior to SDSS-RM. And then the prediction is in blue and magenta. We're trying to get all these new RM masses up to redshift 4-ish, and then and just like doubling, not doubling, like multiplying the numbers of RM AGN we have. Yeah. So over the past few years, the SDSS-RM collaboration has published many results from the SDSS-RM paper data. And so the first plot here is our final black hole mass versus redshift plot. So we have measured all these lags. There's about 300 lags total measured, and they might be from the same quasars. So there's about 300 new black hole mass we've measured. And from that, we really learned a lot more about the complicated dynamics in the broadline region or in the ionization process in the inner part of the AGN. So I'm not going to talk about all the different results. Well, one thing that really got me interested into working on my current project is that we found that the accretion disk size that was observed is always like about 50% larger than what was predicted from a thin disk model. So we just newly got these new constraints on accretion disk, and So with a survey like SDSS-RM, we're really pushing the limits of previously known physics by just gathering a lot more data and doing it a lot more efficiently. For the first time, we can answer questions like, what is the distribution of supermassive, of black hole mass across redshift, or what is the structure of accretion disk? Is our accretion disk models correct? And all these connection from black hole physics to galaxy evolution and formation. So what really I'm looking forward in the next few years is Rubin LSST data. So I really believe like LSST will revolutionize the whole like RM field, because because there's so much more data that will be gathered. So the main survey of LSST will be monitoring the south sky every few days across all these 6 bands, U, G, R, I, Z, Y. And a lot of these skies, there's still a lot of AGNs to be selected with just photometric data, because with LSST itself, we don't have spectroscopic follow-up. So there are open questions like, how do we select AGNs out of all these photometry data? How do we classify them? How do we estimate redshift out of them? And then in general, what does AGN variability look like? Yeah. But really, the exciting part for doing reverberation mapping is the deep drilling fields. So the deep drilling field will take up about 5 to 7% of the total survey time, and it will be focusing on 5 deep drilling fields, and each of them are about 10 degrees squared. The cadence right now is planning to be about 1 to 2 days over the whole 10 years. So there will be like 10K visits on each of the deep drilling fields there. And then it's also a lot deeper than the main survey itself. So one thing to know that the survey strategy has not been finalized yet. So we don't really know what exactly data would we get. But just to quickly cross-reference with SDSS-RM, right? This is the total field of view is about 7 times wider. There is almost 15 times more AGN that is expected to be monitored at an even higher sensitivity. And then the cadence goes from, say, 6 days to 1 to 2 days. So we will have a lot more high quality light curves from LSST compared to previously SDSS-RM. And SDSS-RM already gave us so much new and exciting results. So I really believe that LSST will even push that limit even further. Yeah. So there's a big problem or a small problem is like with these kind of new exciting data, many fields in astronomy are not really used to this kind of data value, right? Including the RM field. So we have a few ways of measuring lags with RM surveys. And none of them are really designed for a large survey or scaled properly to a wider survey. So one way to measure lag is you can do a simple cross correlation between the two light curves. It's a very simple calculation, but it is also known to be less accurate. To do like cross correlation on a set of light curves, say in a single deep drilling field, would take maybe days or so using current code that were developed. So it's still not too bad. But the other method of doing RM is doing these MCMC fitting onto a certain accretion disk model. And this gives us a little bit more direct constraint on the black hole parameters or accretion disk parameters that we're interested in. But each of the fitting will take maybe 1 to 2 hours. And to go through a single deep drilling field might take up to a month. So we really need a faster way of doing reverberation mapping in the era of LSST if we want to take full advantage of the data we have. So let's think about how do we usually learn physics from data, right? We have some sort of theoretical model, and we have some observations that could be used to prove or disprove the theory we have. But it's not always so simple, because in this case, we have a very complicated physics model. We have to consider things like accretion disk geometry, general relativity, reprocessing physics, and then maybe also magnetic field. And then on the data side, we have this high-dimensional light curve that doesn't really directly tell us about the accretion disk itself. So how do we infer physics from observation? Yeah. So this is the problem. This is the basis of a method called simulation-based inference. So if we cannot directly compare our data to model, maybe we can make some simulations out of the theoretical model we have. So say you propose some sort of accretion disk geometry. We simulate some light curves based on that geometry and then compare the light curves from simulation to the light curves from our observation, and then kind of get a posterior. So yeah, so this is simulation-based inference, or SBI, is not a new thing. People have been using it for ages already. One example is, for example, we can directly compare the light curves here and the light curves here, but also to simplify the problem, we can generate some summary statistic based on the data and then compare those instead. So this is, for example, in the case of AGN light curve, we can compare the magnitudes of variability or the characteristics timescale of two different light curves. SBI is also often used in cosmology because we have a lot of statistics that we got from, like, say, a CMB map. Yeah. Because data and models are both getting more and more complex as we discover new things, there is a new, it's increasingly common to start using machine learning to actually find the pattern in the data efficiently. So this is what I'm using right now, doing SBI with deep learning. So the idea is that we have a certain physical model, and then we make some simulations out of it, so simulated data, say, light curves. And then we train the unsupervised learning neural net to learn the representation between the black hole parameters and the simulated data. And then using that, we kind of map the black hole parameters into the simulated data and use the trained neural network to compare our observations, and then to generate the posterior from that. So I'm just going to put some context into that workflow here. So I'm working on a toy project here. I'm using SBI for continuum RM. For the simulation itself, we have a simple accretion disk model. We make the light curve. So the light curve is like this high dimensional array. And then we feed that light curve into our design neural net. So the network is in two parts. The first part is a summary net where we extract some summary statistics from the high dimensional light curve. And then we feed that summary statistics into a density estimator called the mass autoregressive flow. And then once we train this neural network, we can apply new observations and get a posterior from the trained neural network. So for the simulation, we follow a very simple setup. We have an accretion disk model that is governed by 3 different parameters: the black hole mass, the black hole accretion rate, and inclination. And then the accretion disk itself is a black body, is a black body disk that is irradiated by a center X-ray corona here. So this is like the temperature profile of the accretion disk. And then because of this setup, we can kind of calculate the response function or the transfer function that makes the lag from the driving light curve to each of the observed light curve in each band. And so you can see that the lag here, so this is the driving light curve. And then with each of the transfer function, we can compute the smooth and extended, like smooth version of the light curve in each of the band. So this is an example of the simulated light curve. For a very first try of the project right now, we're using light curves with no gap at all. So we simulate these damp random walk light curves, apply the transfer function, and then just use that as our input data to train from the black hole parameters to the light curves. And one thing is that we put in a 1% Gaussian noise into the light curve itself. So to make the light curves a little bit more realistic. So the next step, we train our machine learning model, right? So we want to learn what is the representation between the black hole parameters and the light curve. And so we do this in 2 steps. First step, we use a LSTM network to reduce the dimensionality of the light curves. So the reason is pretty simple. The light curve itself is a 180 by 7 array, so it's like giant. And then we want to get 3 black hole parameters from that. And so the mapping from this high dimensional light curve to the 3 black hole parameters would not be very efficient according to the current structures of like machine learning networks. And so we feed the light curve into a LSTM network first. And so LSTM is a recurrent neural net that is designed to learn temporal signatures in data. So how it does it is that with every input, so every new data point in the light curves, it tries to decide how much of it to retain and how much of it to pass on to the next step and how much of it to forget. And so the idea is that you are trying to learn how a light curve would go from one data point to the next and then to the next. Okay, so after we have the LSTM network learn how AGN variability is like, we feed it through another layer of neural net is just to further summarize the features that we got from the LSTM network. So this is, I think it actually makes sense using LSTM because AGN light curves are usually well modeled by damp random walk, and this is the assumption we're using right now. So the damp random walk itself is an autoregressive process. So the light curve under the characteristic timescale kind of still knows what's going on prior. And then after the damping timescale or the relaxation timescale, it becomes a random walk. So using an LSTM kind of is designed to study these kind of structure. Yeah. And the second step of the neural network is we feed the prior and then the simulation into a deep neural net that is by design invertible. And we do this by using a method called the mask autoregressive flow. So the idea is to learn, so the idea is to use different different equations, like to learn from a simple simple distribution to a high dimension density, high dimension distribution. And so by design, it is invertible because it chooses the functions that are invertible, for example, a Jacobian. And the reason why we want to do this is that we want to get our posterior from our observation. So once you train an invertible network to go from the prior to the simulation, you can also do the same thing and get the posterior from the observation. Yeah, so I know a lot of these machine learning or deep learning networks don't get the exact same thing. Like you've probably seen generative AI that made very creepy human faces before. So this is a different kind of generative AI that does things slightly differently. Yeah. And then so the final step is just to feed in the observation to the trained neural network. The great thing about SBI in the framework we're using right now is that it can be reused for as many times as you want to evaluate new data without training the network again. Yeah, so for our toy experiment, SBI performs pretty well over a very wide range. For the prior range listed here, we plotted the truth versus prediction of all the 3 parameters we have. And then we can somehow constrain inclination to about a few degrees, and then black hole mass and accretion rate to about 0.1 dex. So these kind of, in RM, like a lot of the systematics related to a lot of other things like, say, accretion disk model, and just like very different types of objects is maybe will give you a systematic uncertainty up to like 0.2 or 0.3 dex or above. So this is pretty good. And then unlike a lot of machine learning or deep learning method, SBI itself actually can produce a uncertainty estimation. And yeah, so this uncertainty is directly from evaluating the posterior from the trained network multiple times. And so, yeah, so this is the invertible network I was talking about. You can draw posteriors from this to kind of go back to the original black hole parameter and see how wide of the uncertainty is. And so here I'm plotting the difference between the prediction and the truth, and then over the uncertainty provided by SBI. And you see all of these histograms are basically consistent with a Gaussian of unity width. So then this means that our SBI algorithm is actually producing reasonable results. Yeah. So SBI also can produce pretty much consistent results compared to other methods. Here I'm just testing on a few single cases here because some of these other methods takes a long time to run. And so in one example here, we kind of see what we already know about the strengths and caveats of the other methods, right? So ICCF is pretty fast. This is just doing the cross correlation between different light curve streams. But also it's like, it gives a much wider distribution. So it's overestimating the uncertainty, and also it's a little bit less accurate. And the other method, Javelin, fits the light curves onto accretion disk model and through MCMC. And because it doesn't consider proper correction to the transfer function, we often see that it is underestimating this size. And so the code that I think is the best to compare to is CREAM. CREAM actually models the full transfer function in an accretion disk model. And so it is most consistent, and it's also because our simulation setup is most closest to CREAM as well. Yeah. So one major advantage for SBI in future surveys like LSST is that it is very fast. So after you train the neural network using the simulation, you can do this drawing the posterior unlimited times with almost zero time. And so this is called a amortized posterior. You can reuse a trained neural network multiple times. And so compared to other methods like CCEF and Javelin, to evaluate the whole single deep drilling field will take like maybe minutes. So you can really compare, you can really do this simulation, you can really do this evaluation quick, and also you can evaluate your light curves on different types of, say, accretion disk models. Yeah. So the bottleneck of the time with SBI is actually generating the simulation, depending on how complicated your simulation is, or how many simulations you want to generate. It might take a lot more time. So for here, we are just using a very simple accretion disk model, but you can go full on with like a numerical, hydrodynamical model if you want. Yeah, and the training itself takes like maybe a few hours with 1 million set of light curves and black hole parameters on a single GPU. So it's not too crazy. Yeah. The other thing that SBI is really good at is that it can be a generalized framework to compare different kinds of accretion disk models. And so, with the current SBI code development, you can basically swap out all the simulations you want and just run the whole training seamlessly for different kinds of accretion disk model. And this is really important because we know that currently our accretion disk models are not perfect. For example, observations from SDSS-RM and OSDES, which is the DES continuum RM campaign in the supernova field with DES, we find that accretion disk size are usually about 50% larger than the predicted size by the general thin disk model. And then we also see that hypervariable AGN may be explained by alternative reprocessing models. So say they have a thick disk or they have some sort of hemisphere geometry where different parts of the accretion disk is doing different type of things. Right? We also know that AGN variability is, we also really don't know what the driving mechanism of AGN variability is. So in the light curve I showed here earlier, you can see that the UV and the optical light curves behaves really well. Like you can see that these light curves are correlated. But if you look at the X-ray light curve, it's a whole mess. Like it doesn't look like any of these, right? So there are recent simulations that show that when you inject extra X-ray photons into accretion disk models, a numerical simulation model, you don't really see its effect in the UV variability. So maybe X-ray is not the major driving force of UV and optical light curves. So hopefully LSST will help us answer all these questions in the future. There's a lot of open questions in the field right now, and with more data, it will be really great to try and tackle some of these questions. Yeah, so this brings me to my last slide. I think LSST is super exciting because it's gonna monitor so many more AGN in the next decade with better data. And we really need to try and develop new techniques like machine learning and deep learning to kind of do better science, right? Like it's a tool for me, like to advance science. Yeah, that's it. Thank you.
Questions for Jennifer?
Thanks. Can you go back to the figure with the black hole mass versus redshift? I think it was from SDSS. Back quite a few slides. Yeah.
Let me just scroll through.
I was just curious because what it, I think it was more like a scatter plot. And what I noticed was, I don't think it was this one. It was black hole mass versus redshift on the x-axis. Yeah. But maybe go forward a bit. Let's see.
Oh, do you mean one of these?
No. It was towards when you were talking about SDSS, the results from SDSS-RM. Yeah. Anyway, I'll just ask about it. What I noticed in that plot was that at low redshift, there aren't very many very massive black holes. So you were seeing more of the high mass black holes at high redshift and fewer at low redshift. And is that just an indication that they're not feeding? Is that just a supply issue, do you think, or?
Luminosity plot? Oh, here? Oh. I think this one is the luminosity versus Z. Yeah. So
Something like that, yeah.
Yeah. So most of this is a selection effect. You just, yes. So So for a higher redshift stuff, you can only look at brighter stuff, and so it's mostly a luminosity effect.
And there just aren't bright stuff at low redshift because there are just fewer
rare.
AGN in general. Yeah. Okay.
Thank you. This was a really cool talk. How does SBI deal with stuff that isn't predicted by simulations? So if you give it a bunch of actual observations and you have some things that look like stuff in the simulation, but maybe you have a couple things that are a little weird, does it just give you big error bars, or like how does it tell you that it doesn't know what that is?
Yeah, so in cases where it's similar enough, it will give you the best, so SBI basically gives you the best guess it has based on the model you give it, right? So if you give it completely different things, say you give it a light curve that is not a damp random walk at all, it's say a sine wave or something, then it might it might just not converge, and so you don't have a result out of that. So like it's quite important because like when we're doing science, we want to know if it's the machine learning method is just giving us any answer, right? Or versus like if it's giving us actually, this you shouldn't trust this answer at all.